Today's lecture, this is going to be kind of intense, by the way. We've got a couple of intense few days coming up because I can kind of tell last time you folks kind of look at it, so I get some feedback from you on what's going on. So there's two things about all of this. Now that we're really kind of in more of the morass of quantum mechanics, I know this is way unfamiliar. We're doing things with mathematics, these eigenvalue equations that are way unfamiliar. Okay, to ease you, just remember, none of this gets more complicated than the derivative of sine or the integral of sine. You know, on that level. You know what I mean? Nothing is harder than that. But at the same time, these eigenvalue things are probably very unfamiliar. One of the reasons for videos, when it comes to quantum, I wish I could just say, oh, it's like when the fish runs up a stream, and then you're like, oh, well, I can answer any question you ask now. That will never happen. So when it comes to quantum, no one really ever gets this, and I've never heard of anybody coming up with some pedagogical paradigm that, you know, oh, well, it's just like when a monkey swings from a tree, now I can solve that expectation value. That'll never happen. When it comes to quantum, you know, there's another way to try to get things through on hard stuff is to do it over and over and over and over and over and over and over again. Guess which one quantum belongs to? Do it over and over and over and over and over again. That's why I have long problem sets. That's actually one of the reasons for videos. To get this stuff, I actually would strongly suggest just watching the video over and over and over again. I don't think, in terms of my own mistakes, it's not been too many. It's not been perfect, but not too many. So if you're struggling, you kind of should be. And the way out of it is to watch the videos again, look at the homeworks again. Anyway, now because I kind of felt a little bit of we're getting kind of lost vibe, I'm actually going to slow down a little bit and just review uncertainty, because there's a tremendous number of concepts well up in here that we've gone over and will go over in the future. It encompasses a bunch of stuff. One is, now, okay, this is the kind of BS-y stuff that unfortunately humanity inserts into everything we do. Multiple names for the same thing, and I can't help myself, but I notice I'm accidentally using multiple names for the same thing, and I can't help it. So, so just to remind you that we have operators. Okay, we only got one word for those, but the Hamiltonian, the one for energy, seems to be special. So that one gets its own symbol. Wave functions, all right. We have 3 words for them. This is like Chinese class. 3 words for them. Wave functions, eigenvectors, and eigenfunctions. Eigenfunctions because of the eigenvalue equation, and let's, you know, actually, you notice how I put different wave eigenvectors here? Because we have different operators, like we have momentum, we have position, we have angular momentum in the x direction, angular momentum in the y direction, angular momentum in the z squared direction. We have so many operators. You've only seen a few of them. So that's why I put 1 to represent multiple operators. And all right, so let's just pick on operator 1, maybe that's momentum. And it works on its eigenvector or eigenfunction, and it returns an eigenvalue in the eigenfunction. There you go. And of course I had a question saying define all these terms. And if you just wrote eigenvector, eigenfunction, wave function, operator, eigenvalue, then I just gave you full credit. That was just a throwaway. But anyway, so eigenfunction, because eigen means the same, so the function returns. And if you get this behavior, you've done the problem correctly. And if it doesn't return, then that means that this is not actually an eigenfunction of the operator, assuming that you haven't, messed up a derivative. So anyway, eigenvector, I'll try to show you why we sometimes use that word. It actually is meaningful, but let's not worry about it today. Wave function is also an eigenfunction or eigenvector, but it just, if I start using this word, I'm usually describing the eigenfunctions of the Hamiltonian. So this word is biased. Just like I have a separate symbol for an operator, I tend to have a separate symbol for the eigenfunction of the Hamiltonian, but it's not absolute. again, it's like language class, but it's unfortunate, but this is a thing, and you'll see this. You'll see it in textbooks and whatnot. So anyway, and I can't help it. I noticed that I wish I just stuck with one word and just really stuck on it, but I didn't. So anyway, okay, so uncertainty. Okay, when it comes to uncertainty, I'm just reviewing. There's some simple nuts and bolts to this, which is that if you have an uncertainty problem between two operators, so this is a comma, operators 1 and 2, and I'm not using the Hamiltonian just because I'm trying to be generic, that's when the commutator is not 0, right? Right? What's a commutator? I do this to my grad students, especially sometimes their first language isn't English. And
It's the first times the second.
Right, and then you permute.
Minus the second times the first.
So remember, whenever someone says, oh, you know about this thing or that, and you don't know, you should always speak up, okay? You look dumber if you try to fake it than if not in science. So, okay, so Chris, fast the commutator is a zero or not. As I mentioned ad nauseum, this can be kind of hard to solve. You know that if this is momentum and position, it's not 0, it's h over I, but that's not really obvious. So the way to do that is often to apply a wave function towards it. Sometimes you do it that way, sometimes you don't. You're going to see other examples. This is how we figured out what these were in the examples that you've seen. Okay, so let's just assume that the commutator is not 0. That means you have an uncertainty relationship between these two operators. And again, I'll pick on position and momentum because that's like the famous one. Okay, so maybe I've asked this and you figure out it's not 0 and you get full points and hey, let's just forget this unpleasantness and just go to graduation. That, I'm not so opposed to that, to be blunt. But now maybe some of you, there are a handful of you who may go to grad school, so let's see a little bit more deeply what this means. Okay, now let me just write down the eigenvalue equation. So if I operate, now when I say operator 1 in wave function 1, I mean that this is its guy. This is its eigenfunction. Now if I'm saying that, then this has to be true. No pulling your leg, none of that. And let's do the same for number 2. And again, I'm using this label to say that this is for certain. Okay, now the problem comes when, here maybe I'll just try to keep moving down. It's kind of like why we have these boards put this way. I don't do that enough. Okay, so if I have an uncertainty relationship between the two, then this happens. And it doesn't always happen, but for the most part. What happens is, let's apply the second operator. And remember, operators are questions, and the eigenvalue is the answer to the question. Where is it? Well, that's x. How fast is it going? That's p, double derivative, right? What's its kinetic energy? Double derivative. Anyway, all right, so what happens is if you have an uncertainty principle, you get this mess happening. No, it doesn't work. The eigenfunction, equation fails. And remember, that's mathematical junk. That's how to think of that. That this just flat out doesn't work. For completeness, let me also point out that if you ask the question that is operator 1, do you get the answer? And the answer is no. Now, look, I have to be honest with you. When you have an uncertainty principle, this doesn't always happen. It almost always happens. Swear to God, I really debated telling you this. It's almost always true that these will fail when you mix and match eigenfunctions, but not always. So I just have to be honest about that. It almost universally fails, but not always. You will. The reason I'm telling you the truth about that, there is one example of an uncertainty relationship in angular momentum where the eigen equation will actually still work. So just heads up. Sometimes these will work, but usually they don't. All right. Okay. So do I have an uncertainty principle? Do the commutator, it's not 0. Yes, you have an uncertainty principle. What does that mean? It means that the functions for one operator almost universally do not work for the other operator. Now, you can ask yourself, well then, if I have these functions, maybe these are positions, but I want to know the momentum, then I can't answer the question. I can't know the momentum. As it is written thus far, the answer is yes. You cannot determine the momentum. Now, as you have already seen, there are slick, willy ways around that. Okay, the way around that is, let's see, what would I do? Okay, so let's focus on this one. Let's focus on this one. All right, the solution would be to take the guy that you're, maybe these are Hamiltonian wave functions, eigenfunctions, so I call them wave functions. So these are like important. Remember that the Hamiltonian is important, its wave functions, its eigenvectors, those are the same thing, are important. We think of those as being real. And I want to know something else. I want to know its angular momentum. Oh, but I did this because I have an uncertainty principle, and I did this and it doesn't work. I don't get this eigenvalue equation doesn't work. Instead of giving up, what you do is you write the wave function you're interested in as a function of the other. Right, so I happen to know what these other functions are, so I write the one, maybe this is the energy wave function, I write it as a sum, as a function of the other wave functions. Now, before this, like, well, what the hell do I do with that? You've seen this already. You have seen this. Remember that in the case of sine, sine kx, which you cannot apply the momentum operator on because you end up with a sine equaling a cosine. No, wait, they're not equal. It fails. What you do is you can write it as a function of others that are okay with momentum. Sorry, I have to think about this. Okay, so you can do that. Now, of course, we have to normalize it. We have to, dot our P's and dot our I's and cross our T's and whatnot. Okay, so here's an example of that. When I can't know, so this is the wave function of energy. Cool, that's useful. But I want to know its momentum. Oh, it failed. It failed. I give up. That's actually not such a terrible way to go. I'd give you a C if you just gave up. But if you want an A, you realize that you can actually decompose it into the ones that are okay with momentum, like EV, IKX, and yada, yada, yada. And then you can get the answer with that. Okay, now that's one way. Another way is to do expectation values. And to do that, so what you would do is you would take, so we're working on this one, and we want to apply the operator that's giving us difficulty. Don't forget to do that. Remember, if in the case of sine is not complex, and you just don't do anything. And here we go. And this gives you the average value, and you're fine. So as much as this is a biz knocker, it slows you down, but it doesn't stop you. You got two ways of doing it, this way or this way. Clearly, this is the way you pretty much always want to do it. It's way easier to do it this way. And the proof that this works, by the way, maybe look at the old videos. I actually showed you that what you do is you decompose this into this form. I actually showed you this, and then I inserted this into this equation, and I showed you how it gives you the proper average. I did that, I think that was like 3 lectures ago, but anyway, don't worry about that. Maybe just trust me that it works, especially if you're still having a little trouble with this. So, okay, one more thing about uncertainty principle. Again, remember, I'm still reviewing because this really, I know this is really something here. If you get this, then you're really in good shape. And remember that when it comes to doing this practically, all it is a matter of derivatives of sine and cosine. That's practically how you do this, which you can definitely do that. Okay, what we covered last time, and I really did mess up the subscripts. I meant to put subscripts. Standard deviation, which is a measure of width, of these two operators is greater than or equal to the 1/2 absolute value of their commutator. Now, the absolute value, by the way, comes about because, and don't worry about memorizing that, it's kind of funny. If this commutator, for one, we assume it's not 0, or why are we talking about this? Remember, if it's 0, we have an uncertainty principle. That's what we're talking about. So let's assume the commutator is not 0. The reason there's an absolute value sign is because if I wrote it in reverse, it'd pick up a minus sign, right? If I wrote 2, 1, then whatever this is, it would be minus that from 1, 2, right? So anyway, absolute value sign, get rid of that. Now, greater than or equal to half of that is actually a geometry proof. And I'm not going to show it. It's something you learn in grad school. It's really not too hard, but it's a geometry proof. So it's actually really kind of simple. I just don't want to spend any time on it. And when you see that proof, you're going to understand more why you use the term eigenvector. So, and maybe, I tell you what, don't write this down, but let me give you a little bit of an aside. Let me show you another way to do all this. Let's think of the wave function in x as being this vector. And as I mentioned to you, you want to solve this, you want to re-represent this. You want to re-represent this as a function of the vectors of the other. The other is momentum. Let's say that you have this vector, and this is a p function. What do you do? Can you equate those? Right. So I've gotten one in x, and one is angled. Can I equate those vectors?
Sure.
No. No, of course not. It's pointing in the wrong direction. Right. There's nothing I can do with this to make it equal that. Right? But what if I gave you this too? Here's another. So like I got P1 and P2. Now does that work? Huh? If I add these two vectors, do I get this one?
Sure.
Yes, right. The component in the y direction gets canceled out. That's what we're doing. When I say sine is e to the ikx minus e to the minus ikx, this is basically what you're doing. You're taking things that don't fit, but if you sum them together the right way, they can. And the reason they don't fit is because they work in different dimensions. That's why we call them vectors, because the vectors can point in different directions, and you've got a problem working with that unless you do some, anyways, I'm just trying to visually represent why this right here, why that works. This is just a visual vector representation. And that's why people often use the term eigenvectors. Anyway, so I just wanted to show you that. Now what? Okay, so I've got this thing right here. And, okay, so let's do x and t. And you'll see some others when we get to angular momentum. So that's what this turns out to be. We covered that last time. But notice that means that if let's make the uncertainty in position go up, and that means that the wave function is wide. If that goes up, therefore, the momentum has to go down, and that means when I draw the wave function, here I need to label this. If I draw this as a function of momentum, then it's narrow, and vice versa. So if this is wide, then this is thin. And and vice versa. Okay, last bit, and this hopefully, I'm going to do this, I'm going to ask you to answer some questions for me, because this will really hopefully solidify all of this. And when I draw these very loosey-goosey graphs, it can make this a little too abstract. And I know sometimes that's upsetting, because then I have a homework or an exam where I'm like, now give me a number. And you're like, well, you just drew some squiggly lines. I don't know how to get a number from that. Well, now hold on. Sines, cosines integrate. Look at the cheat sheet. But now let's build some intuition, because that's actually pretty useful. Okay, so let's do a particle in a box, which is mostly what we're talking about today. And you know that's when the energy is infinity, so I'm drawing potential energy here. We're going from 0 to L, so this is in the x dimension. And I'm going to draw a wide wave function, pretty wide one. Okay, now what I want to do is I can create a wave function in momentum, and so the x-axis is not actually x, it's momentum. And, okay, so the wave function will be kind of narrow. Of course, it'll be centered, here, it'll be centered about its average value. Let me, this is actually how European journals express their x-axis. So anyway, okay. All right, fine and good. This is why that's narrow. All right, the squiggly lines, it implies, I'm drawing these squiggly lines based on these principles. But now let's put some numbers to this so it makes a little bit more sense. All right, now, this particle, let's say it's an electron, is trapped in some kind of electrostatic cage. If it goes left of 0, we define some potential energy barrier at 0 and another one at L. Maybe these are the walls of the container, perhaps, whatever. It can't do it. It takes infinite amount of energy to get out of this barrier. It can't do it. Okay, fine, whatever. Momentum. Let's think about what does that mean for momentum. Tell you what, you should actually be able to give me a number. What do you think this number, now you see x goes from 0 to L. Of course you understand that. That's very simple. Okay, let's figure it out for momentum. Let's actually put numbers to momentum. What do you think the average momentum is?
0.
Huh? What if you said something? What if you said the answer?
0.
0. Now for one, that's probably about the only thing you could guess, or you know it. Either way, that's right. And we would also have units of h bar k. Don't worry about that. Of course it's 0. Now think about this. If you're like, well, wait, how did you know that? If this particle, this electron, if it has an average momentum greater than 0, what's it going to do with respect to this box? On average, it's moving to the right, and always moving to the right. Therefore, it's going to, go outside the box. It has to. It has an average momentum of plus something, a meter per second. It can only do that if it keeps moving right more than it moves left. If it keeps moving right more than it moves left, it has to get out of the box at some point, but it can't. Ergo, the momentum is centered at 0. Right? Right? It makes perfect sense. Okay, and same for left. Okay, now, all right. Now, again, this is hopefully very, very sensible. Now, let's take this wave function. Maybe this is the wave function for energy, so we'll call it psi. Okay, is this true? Is this true? Huh? Huh? Yes, no? This is true? No, this is not true for all the freaking reasons I just said. No, what'll happen is the wave function, the wave function won't come back. Remember, this is like a sine. Look at it, it's a sine function. You take the derivative, it's a cosine. No, it doesn't work. It doesn't work. And why should it work? Let's say that this did work. This means that it's not that the average momentum is 0. It is 0. If this worked, this wave function's momentum is not an average of 0, it is 0. Well, what kind of particle is that? Right? So it's a particle that's not only in the middle, it's also perfectly stationary. Well, that doesn't make any sense. I mean, that's nothing. Why would I have amplitude left or right of the center? Unless it could move there. Right? You see, it may have an average momentum of 0, but at any given moment, probably it does have a momentum, because sometimes it moves to the right. It's just that when it moves to the right, it hits the wall and moves back to the left. And it hits the wall there and it moves back to the right. So it can have momentum. It's just, and it averages to 0, but it isn't necessarily 0, because of the simple reason that it's bouncing back and forth. It's like those old video games where there's old tennis games, right? There's a little ball going back and forth. It's exactly like that. So this should fail. it makes sense for this to fail because the average momentum may be 0, but it's not always going 0. So that's why you have to do this the average value way. And then you get the right answer. All right. So anyway, does that help a little bit? All right. So again, the center of the momentum thing is 0. It can move right. It can move left. Of course it does. It's bouncing around this cage. But since it doesn't leave the cage, it's centered at 0. Again, it all makes sense. But because the way I interpret an eigenvalue equation of what is it? What is the momentum? There is no the momentum. There's multiple momentums. Sometimes it's positive, sometimes it's negative. You can't pin it down to a single momentum, which is what this wants to do. So it just doesn't work because it's like, tell me how much money is in your bank account right now and it is always in your bank account?
0.
No, that's someone who's not quite as poor as right? So that's a dumb question. Well, it goes up and down. And I'm like, no, I don't want to know that. Tell me the amount of money that's in there now and has always been and will always be. And you should look at me straight. No, it doesn't work like that. Sometimes I have more money, sometimes I have less. You can't ask me how much money is in there now because that's what's always been there and what will always be there. That's a nonsense question. Right, exactly. That's why it fails, because it's a nonsense question. Yeah, we're okay. Well, anyway, that's the best I got. Again, if you're still having a little trouble with this, watch the video again and again and again and again and again and again. Moving on, I want to talk a little bit about, oh God, now remember folks, keep me on track on time because my watch again is broken. Now we're going to go over what we call, this is like a different, I think we're in a new chapter now, by the way. This is what we call applications of quantum mechanics. I think that's the title of the chapter. You know, I kind of don't care too much. Especially as the class evolves, I try to get feedback from you folks, just even if I just look at you, and that tells me what I need to be doing next. Okay, we're going to be doing, so we're going to wrap up some things today. Then tomorrow we're going to do multi-dimensional quantum mechanics. And after that, then next week, I think we're going to start doing potential energy. And that's going to definitely crank up the knob quite a bit. But today, again, I'll call this applications. Don't worry about this. Applications in quantum. And we're still going to be working with flat potentials. But like a particle in the box, you notice that particle in the box actually does introduce potential energy in a snarky way. Inside the box, the potential is 0. Outside the box, I actually have potential energy. It's just infinite, so you just don't ever look outside the box. So that way, we're still doing free wave problems. Also, we're doing potential energy problems simultaneously. It's kind of weird, but it has the benefit of being very easy. Okay, so anyway. Now, let's still just assume, even when I'm doing some snarky potential energy problems by like particle in a box, it's still, the Hamiltonian we're still dealing with is still this. Just kinetic energy, and again, we're in one dimension, is equal to E. Now again, in math speak, mathematicians like to put things this way. You should know that this is meaningless. You need to put a wave function in front of it. I'm using wave function because this is the Hamiltonian. Otherwise, I would use that other C or whatever the hell that is. Okay, now go to a math class and say, hey, what is this? Now, if you don't want to spend some time on homework and are looking over the exam on Friday, I can actually show you how mathematicians straight up solve this. And again, I want to do, if you want to, that will hopefully be like, yeah, none of this is all that bad. It really isn't. Okay. It turns out that, again, if this is math class, you find out there is one answer to this. This is the answer no matter what. But notice, it's kind of, again, I like that word snarky. it's open-ended. I have this A and B, I haven't defined them. I have this K. Now you know that's momentum, but I haven't really defined it. Maybe it's like 2 pi over L, and it's 2 pi over L. So the thing is that this will always work with this, and in fact if you do that, so try it, what you get is Hamiltonian wave function. You get h squared k squared over 2m, and you'll get the wave function back. So maybe try that on your own. Try to, since this is the eigenfunction of this Hamiltonian, you don't need to do it the average value way. You can do it with the eigenvalue way, and you will be able to untangle the A's and B's and blah, blah, blah. Don't even worry. A and B have normalization. You can do this. In fact, I think you've already done it on a homework or two, or done it in class. Okay, fine. Now, it turns out that in quantum, even as a faculty member in physical chemistry, I actually will use what I'm about to show you in a professional setting. So I know that this is like your first introduction. Usually we're showing you like childlike examples that no one actually ever uses. Well, that's, again, remember, we're on the border of grad school. So I actually do some of the calculations I'm about to show you. Okay, so if this is the solution, you can apply it to different situations where there's potential energy, such as this guy that we've seen a couple of times now, which is the particle in a box. Particle in box. Now, don't write this down, but we're also going to cover next week, we're going to do this one. This is X. We'll say it's a 0. We'll do a finite barrier. We'll do a finite barrier problem. We can also, step. That's a step potential. The finite barrier is like this. So we got a couple of these. We can play with potential energy and still work with this solution. And when I throw a particle in a box, a step potential, or whatever I come up with, all you do is you start with this and you start to whittle away at the A's and B's and K's. Once you have A and B and K, you're done. Then what you do is you plug it back into the Schrodinger equation, you can get the energies. Remember, I told you at the very beginning, the damnedest thing about quantum mechanics is you actually figure out the wave function without ever solving the Schrodinger equation. You almost never use the Schrodinger equation to solve it. You know some general math principles. I know that this is true. I then flesh out the A's and B's and K's by looking at the problem, and then I can use this to double check the answer, and I can use it to get the energies. By itself, and one reason I have to do that too as well, I mean, look at this damn thing. I have a function which is unknown, and I have energies which are unknown, and I have one equation, right? So you weren't ever really going to be able to solve this. One equation with two unknowns, you were screwed, right? So, okay, anyway, so I've got this Hamiltonian. I can very snarkily apply this to situations with potential energy, like a particle in a box or a step potential. But how does that work? How does that work? I mean, how am I on time? Again, my...
7.
What's that?
7 minutes.
Okay, 7 minutes left, or?
Yeah.
Okay. Okay, so, yeah, sorry, that's my dad's watch, by the way. He passed away about, 11 years ago? So, I have to spend like $100 a year to keep that watch going. Oh, but anyway, okay, so what do you do? What do you do with this information? So you got this wave function, and now I'm going to throw something at you like a particle. Let's do particle in the box. I'm going to throw this at you. Okay, what do you do with it? Well, it turns out, remember I said about 2 weeks ago that wave functions have to do a couple things. They have to be smooth and continuous. And I remember I even told you that's actually really important. It is important because that principle is how you get the A's and B's and K's. Okay, now, in the case of infinite, you know that the wave function has to be flat outside of the box, and then it can be something like this inside the box. That's okay. Okay, to make that happen, to make that boundary condition work, means that at x equals 0, now remember the purpose of this is to take what we know to be the solution a e to the ikx plus b e to the minus ikx, We're trying to make that work for real. That means I have to figure out what A and B and K are. Okay, at x equals 0, the wave function has to be 0. Okay, so 0 is A e to the I k 0 plus B e to the minus I k 0. What's e to the 0? 1. A is equal to minus B. All right, you should be able to figure that out very quickly. 0 is equal to A plus B, A is equal to minus B. Okay, therefore, the wave function is A e to the ikx minus A e to the minus ikx. I just picked on A. Actually, I should replace A. I should replace it with the normalization constant. In fact, that will actually give me pretty much exactly what I need to know, which means that this is obviously sine. This is obviously sine kx. Now, I know enough math to tell you that when you have this symmetry, e to the ikx minus e to the minus ikx, it's a sine function. I know that I need a 1 over 2i there. It's not important. That gets absorbed into the normalization. That's actually not important. Now, I know that's not something that you know. You have to learn that. You have to hear it for the first time. You just heard it for the first time. 20 years ago, I heard it for the first time. So when I see this symmetry, I know that the answer is sine. It's something you just kind of have to know. If this was a positive, if for some reason the boundary condition made this positive, cosine, exactly. Now again, I don't know how you would just spontaneously know that, because I know in your mind, I was once your age 2, I know that you want this to be 1 over 2, you want me to show you that this is 1 over 2i, and then for certain it's a sine function. I can do that by normalizing it, but I can just tell you it's a sine. Okay, last thing is, how am I doing on time again? Sorry. 4. Okay, I got enough time to show you. The next thing is I need to figure out k. Right? I know k is momentum, but right now it's just too nebulous. It's just too nebulous. I need to figure out a little bit more about what is k, and then I've got my answers. My answer, by the way, will be the energies as determined by the Schrödinger equation. Okay, what can I do? What can I do to figure out what k is? Now, I figured out that I had a sine function by this. At x equals L, the wave function is still 0, right? So guess what? Now instead of going back here, I'm just going to save some time. Okay, let's, at x equals L, okay. How do I make that work? So x equals L. So sine kx, sine kl, k is what? So remember, I just made x equals L. What is k equal such that the wave function looks like this and it's equal to 0? Huh? 2 pi? No.
No, the k times L has to be
pi. Yeah, it's got to be pi. Oh, it has to be what? Pi or?
2 pi.
Oh, right. Now this would work too, right?
N pi?
N pi. Right, there you go. N pi over L. That's exactly right. Okay, therefore, now you see what you've done is you've applied boundary conditions. Okay, there's a normalization constant, which by the way we've already done. So I'm just going to write that answer. There you go. Right, again, there are stipulations on smooth and continuous, boundary conditions. It's all really quite obvious. When I throw problems at you, I will make sure that you know extremely well what the conditions are. That allows you to figure out the wave function. But now, guess what? Guess what if I do this? Right? I'm going to be able to figure out, I'll solve this next time, so I'll just leave this to you. So having figured out the wave function, based on general knowledge, a little bit of math knowledge, a little bit of me just kind of looking at this and making sense of it, I'm able to figure out the wave function, and I've properly normalized it. We've talked about that before, so that's why I'm just throwing that up at you. And what that means is now I can apply the Hamiltonian, and what I get is h bar squared, n squared, pi squared. You see, it's just the innards. The innards are squared. I've got 2m from the Hamiltonian, and I've got an L squared. And if you want to, the book doesn't like h bar so much. So what the book does is it just takes out the 2 pi. It does simplify it. It's kind of nice. Sorry, I forgot the side. Forgot the little side. Sorry about that. It's not ideal. Here, let me just erase my mistake. Like the Trump administration. Anyway, so there you go. There you go. So there you go. That's the energy. Okay, real quick. And of course, n has to go from 1, 2, 3, dot, dot, dot. Real quick, I'm out of time, right? I'm out of time? Okay, real quick. We have a special word for n equals 1. It's the something state. Ground state. N equals 2, n equals 3, n equals 4. Excited states, right? Because they have higher energy. Okay, folks, I know this was hideously intense. I warned you. Next time, I'll review this and we'll